take a break, this cake to make. Plus I had it in the bag since Jake the Snake. Duck Jake and the Snake, keep the grass cut. Look out for Giants and Yankee jackets with the cheap shades.
This final section is about Taylor series. Okay, so in this section, we're going to be going over Taylor series in relation to sequences or series. Hold on. Backing up. Taylor series is kind of a blend of what we've learned about Taylor polynomials and infinite series. There we go. That's what I wanted to say. So what we're going to have is something that looks like this. And this is going to be, as we've seen before, a0 plus a1 x minus c to the 1 plus a2 x minus c squared plus, and I'll write one more, a3 x minus c to the third, and etc., right? And then, as we've seen before, though, the Taylor polynomial looks like this. So we would have f to the 0, which is just f of a in this case. And then remember when the Taylor polynomial was centered around a, and then we have x minus a to the 0 power plus f1, or f prime of a over 1 factorial times x minus a to the 1 power plus f double prime of a over 2 factorial x minus a squared, and I'll do one more, f triple prime evaluated at a over 3 factorial times x minus a to the third, and so on, right? So looking at these two equations, the expanded forms, they actually kind of look similar, right? Because this term here, that actually just becomes 1. So what we have in front is a constant, okay? And then here we have some term in front. Remember, this is just a constant, this is just a constant, in front of some parentheses raised to the 1 power, plus same thing here, these coefficients here, and then we have x minus something raised to the 2nd power, and so on. So, we could kind of write little, like, again, mini equations. So we have 0 factorial is just 1, okay? So we have a0, a sub 0 equals f of a. We have a1 being equal to f prime of a over 1. And then we have a2 equaling f double prime of a over 2 factorial. And I'll write the last one equals f triple prime of a over 3 factorial. So what you can consider, though, because here we had a being our center, right, for the Taylor polynomial, a was the center, a is the center, but you can also, you can put any letter to represent the center. That's just what we used when we were working with Taylor polynomials. But what if we use c, right, for the infinite series, for our power series? So c is the center, right? Remember, we just went over that in section 11.6. So let's just replace the a's with c's and see what we get. So then we get f of c, f prime of c equals f double prime of c over 2 factorial. And the last one, f triple prime of c over 3 factorial. And I just replaced the variables. It's the same thing. They both represent the center. So I just switched the letters. Anyways, from this, we can see that our a sub n, so to get these terms on the left, that equals f to the n power, right? F, the nth derivative, I guess you could consider it, because when we had like a sub 0, that's our original function. A sub 1 was the first derivative, a sub 2 was the second derivative, so you see how that's connected here. And then evaluate at c, which is the center, over n factorial. Okay, so this is an important relation that we just derived here. Okay, I'll move on to the next slide so we have some more room. So what this is called, so we can basically represent the Taylor, this is the Taylor series expansion. This is what it's called. So let's say we have this, right? And then instead of a sub n, which we said was this following thing over n factorial. And then we have a x minus c to the n. So we kind of infused the Taylor polynomial form into the sequence, right? The a sub n, because this thing we said was a sub n, and we blended it into the series form. So basically, and again, just to reiterate, this is our radius of convergence, which would give us our interval of convergence. But this is called a Taylor series expansion. So Taylor series expansion. And then just as a reminder, Maclaurin series, that didn't turn out too well. Maclaurin series is when our center is 0. So that happens when C equals 0. Okay. Okay. So then we also have another important relation. Okay, I don't know why the whole screen moved. Oops, went over too far. Okay, there we go. So if on the following, so if on this interval of convergence, right, because we've seen this before, this is our interval where r is greater than 0, there exists, so this is another one of those important statements, there exists a, they use k, and I'll just use it too, there exists a k greater than 0, so some number, some positive number, right, such that the f to the k derivative of x, the absolute value of that is less than or equal to k. So what this is saying, well, I'll write out the rest and then I'll explain it. So we have our then, our declarative then, f of x is represented, this stands for represented by Taylor series. Taylor series in the interval. In the interval. Okay, so what this means is that if there exists some positive number such that all of the derivatives, all of the absolute values of the derivatives of the certain function stay below it. So this is an upper bound, right? So that would be, remember our capital M? This is our upper bound. So if there is an upper bound to all of the derivatives of a certain function, then this one function could be represented by a Taylor series that looks like this. This is our Taylor series, okay? Okay, and then in the interval, so the interval, as I said before in here, the interval would be C minus R to C plus R. Okay. All right. So now I'd like to move on to a different topic. Well, not really a different topic, but yeah, it's kind of related actually. So what I'm going to say is that let's say our f of x is sine x, right? And as you know, sine x is kind of just the derivatives of it. When you do the first derivative, that would be cosine x. And then when you do the derivative of that, that's negative sine x. And then you go to negative cosine x, which turns back into sine x. So it kind of just goes in a cycle, like a circle, right? And all of them, sine and cosine, cannot exceed 1, those values. So I guess 1 would be its bound, right? It's bound for its absolute value. So anyways, the whole point behind my explanation there was that it can be represented by a Taylor series. So, in fact, the Taylor series is going to look like this. We're going to have something like this, negative 1. Yeah, and we have this factor of negative 1 because sine ranges from negative 1 to 1, right? And then we have x to the 2n plus 1 over 2, well, that's supposed to be a 2. 2n plus 1 factorial, okay? And this is equal to, this is going to look like x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial, and so on. And there's a derivation of this in the book, I believe. But you can probably, I mean, you could just derive this by doing the Taylor series expansion, where you have like the f the f to the, or the first derivative of f over the n factorial, and so on and so forth. And you'll just see that the even terms, like when n equals 2, n equals 4, n equals 6, those just cancel out. So that's why we're only left with the odd terms here. Okay, and then on the other hand, we, so this was like kind of like an odd function kind of thing, if you want to think of it like that. But cosine is going to only retain the even ones. So this is like the opposite of sine, basically. So then we have x to the 2n over 2n factorial. Okay, so this is going to look like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so forth. Okay? And then the last one that I want to kind of emphasize is the e to the x. And I think I did this on a previous slide too, but I'll just write it anyways. So this, again, this can be represented by a Taylor series of x to the n over n factorial. And this is just going to be our 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial, and so on and so forth. Okay? So those three are pretty important, and we can, from there we can kind of manipulate other functions as well.
Getting dollars, gorilla bodysuit with the airbrush muscles like Giant Gonzalez. Keeping an eye out for impalas.